Okay, so in the previous video, I sort of gave a fairly long-winded definition of utility functions, budget constraints, and then just sort of kind of talked a bit philosophically about sort of why it is we're sort of having this particular conversation. Long story short, we need a model to explain consumer decisions if we're going to later on fully understand the role and impact of policy on consumer decisions. And of course, ultimately, when we talk about the GDP of an economy, consumption ends up being one of the, if not the most important parts of GDP. Gross domestic product is actually how much people consume. And even when we talk about things like investments and when we talk about producer behavior, very often a lot of these kind of sort of consumption-like mechanisms do a good job of explaining a lot of different types of situations in which someone is optimizing. It just happens to be the case here that we're talking about optimizing consumption. So again, the idea that economists have is that consumers are governed in a sense by utility functions. Everybody has a utility function, and the utility function has within it certain preferences. And those preferences are manifest when we actually consume things. So when we consume something, we feel our preferences. Ultimately, we end up buying the goods that we like to buy, and we avoid the goods that we don't like to buy. That is, in a sense, us simply being governed by our utility function. So I consume some things, they make me very happy. I will tend to want to consume them. Other things make me less happy. I will tend to want to consume less of them. Again, nothing crazy. This should make a lot of sense to you, but let's sort of operationalize it. Let's sort of formalize this particular idea. Okay, so now I'm going to switch and I'm going to do some non-lecture slides, and let's actually do some whiteboard stuff. Okay. So as we've established, we have utility function. So let's say we have a utility function, which is equal to, and we're going to say x raised to the 0.5 and y raised to the 0.5. So this is a type of utility function that we refer to as Cobb-Douglas. The Cobb-Douglas utility function is known as a well-behaved utility function. I talked a little bit about what that meant in the previous video, but suffice it to say, the idea of well-behaved utility functions is that ultimately they produce what we refer to as convex indifference curves. So we have these difference curves that sort of look like this, and each of these represents a level of utility with increases in utility in that particular direction. And then again, the idea is going to be is that I'm going to be constrained in my ability to consume. And so the goal of consumption is going to be to consume at the highest possible indifference curve relative to my actual budget. So what we normally say is we say that the goal of utility maximization is to maximize by choosing X and Y subject to, and then subject to is my income equals the amount of money I spend on X plus the amount of money that I spend on Y, right? We could certainly write this as a greater than or equal to. So in other words, I can't spend more than my income, but it's actually just a lot easier for us to go ahead and make that into an actual equality there. So I'm going to maximize my utility subject to the budget constraint. So let's give the budget constraint. So we'll say that the price of good X is equal to 2, and we'll say the price of good Y is equal to 4. Okay. And then we'll say that income is equal to 100. Now, or actually, excuse me. Let's say income is equal to 160. Okay. So price of X is 2, price of Y is 4, and I have $160 in income, and this is my utility function. So if I want to maximize my utility, as I said before, what I want to do is I want to consume on the highest possible indifference curve. Now, what does that mean? What that means is that I'm going to have sort of theoretical indifference curves that look like this, but then I'm going to have this non-theoretical budget constraint. It's going to look like that, right? So this is my budget constraint, m divided by py, m divided by px. You should notice that my budget constraint is just created by how much money could I spend if I spent all of my money on good x, that would be right here, and then how many units of good y could I consume if I spent all of my money on good y. And so the idea is that I want to find the highest possible indifference curve that I can afford. And mathematically, this is found at this tangency condition. And this tangency implies that the slope of the indifference curve is equal to the slope of the budget constraint. Okay, that's going to be really important. So the idea here is that the highest possible indifference curve that I could consume is going to be found at the intersection, I'm sorry, not intersection, the tangency of the slope of the indifference curve and the slope of the budget constraint. Okay, now, mathematically, that means that we need to have something that gives us the slope of the indifference curve, because we know what the slope of the budget constraint is, right? The slope of the budget constraint ends up just being the ratio of x to y prices. It's negative because it's downward sloping. Right, that's what the budget constraint ends up being. It ends up just being the ratio of prices. So we need to know what the slope of the indifference curve is. All right, so the slope of the indifference curve is something referred to as marginal rate of substitution, MRS. And MRS is equal to ratio of marginal utilities, right? And then just remember, marginal utility is just the change in my utility of x, or I'm sorry, my utility when I consume additional units of x, and my marginal utility of y is the change in utility of y when I consume additional units of y. What that means is that marginal utility of x, in a calculus sense, ends up just equaling the partial derivative of utility with respect to x. And the marginal utility of y is going to equal the partial derivative of utility with respect to y. Okay? Now, going back to our original utility function, x raised to the 0.5, y raised to the 0.5. So we can do the partial derivative here. So if my utility function is x to the 0.5, y to the 0.5, if I take the partial derivative of that function with respect to x, I'm going to get 0.5 x to the negative 0.5, and then y to the 0.5. Okay, so this is the partial derivative of my utility function with respect to x. So when I take the derivative of my utility function with respect to x, that's what I get. And then I'm going to do the same thing for y. All right. So they're my marginal utilities. Okay. So now I can compute marginal rate of substitution. So marginal rate of substitution is just going to be MUX over MUY. So 0.5x to the negative 0.5, 0.5 x to 0.5, y to the negative 0.5. So we can do some simplification here. Take this away, take this away. We get rid of this x, get rid of this y. These exponents are here. And what we're left with is the marginal rate substitution here is equal to just y over x. So we got some nice little simplification there. This is where I mentioned, I think in the very first video, the exponent rules and taking derivatives of exponents. This is probably more tricky than the actual just calculus of taking the derivatives. So this is probably where people tend to get a little bit messed up. Now, obviously, because the exponents here are equal to each other, things tend to work out a little bit more cleanly. I have some other examples that you can look through where the exponents are not equal. And so it doesn't change the math at all. It just doesn't necessarily simplify as well as this particular example is. Okay, so we have marginal rate substitution. And so now what we got to do is we just have to set MRS to the slope of the budget constraint, which is Px over Py. If we recall, the price of X is 2, price of Y is 4. So we can say that in optimality, y over x is going to be equal to 2 over 4. And so we solve for x and y here. And what we're going to get is that x star, that is the optimal amount of x relative to y, is let's see here. So we move our stuff around, 2x for y. So x is equal to 2y, and y star is equal to y star is equal to x over 2. Okay. So that was first condition. So the first condition is that we need the slope of the budget constraint to be tangent to the slope of the indifference curve. And so we have that. So condition 1 is, in a sense, sort of satisfied. And then condition 2 is that we need essentially to just spend all of our money. So income is equal to PX plus PYY. So we just substitute in, I believe we had $160 in income, price of X is 2, plus the price of Y is 4. We know what optimal X and Y are relative to each other, so we can just substitute into our budget constraint. Essentially what this creates is 2 equations and 2 unknowns. So this right here, this is condition 1. This is 1 equation, 2 unknowns, x and y are unknowns. And then this is the second equation. So we have 2 equations and 2 unknowns. Makes our life quite easy. So x star is 2y. So I'm just going to do 160 is equal to 2y plus 4y. 160 is equal to 8y. Y star is equal to 20 units. And I know that y star is equal to x divided by 2, right? And so x star, therefore, is going to be 40 units. And there's my optimal bundle. Again, optimal bundles are found at the tangency condition between the highest possible indifference curve that I can consume So in this particular example, if I have a utility function of x raised to the 0.5, y to the 0.5, the price of x is 2, the price of y is 4, and my income is 160, then my optimal bundle between x and y is 40 units of x and 20 units of y. That's utility maximization, right? That's utility maximization. So now let's go through another example and let's change the price of one of the goods. Okay, so same idea before. U is equal to x 0.5, y 0.5. Let's do price of x. Let's change that now to 4, and we'll leave the price of y is 4, and we'll leave income also at 160. Okay. all the same as before. We don't have to recalculate marginal rate substitution because that hasn't changed. So marginal rate substitution between x and y, we already know is y over x. Okay, now we can see that the slope of the budget constraint is just 1. So that means that x star is equal to y star. So now, so this is just condition 1. Condition 2 is budget constraint. So 160 is equal to 4, oops. Yeah, that's right, 4x plus 4y. This is equal to 4y plus 4y. And we get 8y, 160 y star is equal to 20. And now we know that x star is also 20. So optimal bundle now is 20 of both. That should make sense to you because what happened is that previously I consumed 40 units of X1, but now X1, I'm sorry, X, I keep saying X1, X is more expensive. And so as a result, I altered my behavior to reflect that particular fact. But like I said, this is how you calculate optimal bundles. You have 2 conditions. You set marginal rate of substitution equal to the slope of the budget constraint, and then we spend all of our money, as we can see right there. Okay. Now, there actually is another way. Some of you, if you've done constrained optimization before, you might have come across what's known as the Lagrangian method. So I actually have this in the slides. So if you go to right here, the Lagrangian method is just the way it works is that you have an objective function that you want to maximize. Here, that's the utility function. That is subject to a constraint. So in this particular example, we can see the price of X is 10, the price of Y is 5, and I have $100 to spend. And so the way you set it up is you set up the objective function, and then you add the constraint on along with the coefficient. That coefficient here is lambda. So lambda times the budget constraint. Okay, so objective function plus the budget constraint along with the coefficient lambda. And so when you do this, what you do is you calculate what we call first order conditions. Again, they're just partial derivatives. So the partial of the Lagrangian with respect to X, the partial of the Lagrangian with respect to Y. What this ends up enabling you to do is to essentially do the same thing as before. And so you can calculate the sort of relative optimal bundles. Here we can see that Y is going to, in units, is going to be 2 times the number of optimal units of X. And ultimately, the optimal bundle here ends up being 5 and 10. And it doesn't matter whether you use the Lagrangian method or if you use the method that I showed you before, you'll get to the same answer. So it's a matter of preference, really. Now, one of the things I want to kind of point out to you is that there's sort of a generalizability that we can have here, because you'll notice here that my preference relation between X and Y are essentially equal. I don't value X or Y more than the other. And we can see that Y is twice as expensive as X. And then ultimately, we can see that I consume twice as many units of Y compared to X. And so the fact that Y is half as expensive as X, and I don't have a preference over X and Y, then I then turn around and consume twice as many units of Y should make a lot of sense in that particular sort of concept. And of course, if the exponents are not the same, then the shares are not going to be as even. So, for example, if I have a utility function that looks like this, and X is twice as expensive as Y is here, we can see ultimately the optimal amount of X is not simply going to be half Y. It's going to be even more than that, because not only do I prefer Y to X here in terms of marginal utility, but X is more expensive than Y. So not only is X more expensive than Y, but I actually want more of it as well. So you should just work through some example of these. I'll post a number of examples of utility maximization and using Lagrangians or the substitution method as I showed you before. This is just a general result to sort of show you if we don't have any kind of actual like parameterization, we just solve these for their general values. We get some actually kind of pretty cool sort of outcomes here, which is basically that optimal X is going to be a function of the exponent on X. That's what the A is here. That's the exponent on X. My income, the relative exponents between X and Y, and then the price of X. And you should see that all of these sort of make sense. So as A rises, I'm going to typically consume more X. As income rises, I'm going to typically consume more X. As B rises, I'm going to consume less X. And as the price of X rises, I'm going to consume less X. So these ultimately actually end up being what we call demand functions. So these are demand functions because they are optimal unit functions, so optimal consumption, as a function of income and prices. And so that's what ultimately makes these into demand functions. So here, this is how we go from a utility function, a budget constraint, and then to optimal bundle.